For our final video of the semester, we're going to talk about the intermediate value theorem and we'll do a couple of examples. So this is section 5.3 in lay. First of all, the definition of the intermediate value theorem. Suppose that f is a continuous function from some interval to r, a to b. So the continuous is very important, otherwise we can't use this theorem. Second thing to point out, f often is defined and continuous on more than just this interval, but we only care about this interval for the purposes of this. So if f goes, say, from r to r, then a and b can be any interval, as long as f is continuous. Okay, so then if k is between f of a and f of b, in other words, well, if f of a is smaller than f of b, k is in between them like this, or if f of b is smaller, it's in between them like that. Then there exists some c in between a and b such that f of c equals k. So this is the intermediate value theorem as we've learned in lecture. And so this is theorem 5.3.6 in lay if you want to look that up. So we're going to do a couple of problems to demonstrate this. One of them, this first one, 5.3 problem 6, was one of the suggested but not required homework problems. And the second one was not part of those. So this one is to show that any polynomial of odd degree has at least one real root. It's very important that it's odd degree. And so you can think of this as an odd degree maybe starts out very negative and goes up very positive. And so it's got to cross 0. Or if it's got a negative top coefficient, it goes the other way. So we're going to look at this formally in a second. But before I start this proof, I do want to mention that there's an algebraic proof of this, which is this is a polynomial of odd degree with real coefficients. And so if we factor it over the complex numbers, it factors into linear factors. And as you might remember from your algebra class, it factors into any complex roots come in conjugate pairs. And so that means that any all complex roots, it must be an even number in total. And so if we have odd degree, there must be an odd number of roots in total counting multiplicity. And so at least one of them has to be real. We're not going to prove it that way, though. We're going to prove it using the intermediate value theorem. So first of all, let's let p of x be our polynomial. So it's odd degree, n is odd here. And so it's a sub n times x to the n plus a sub n minus 1, x to the n minus 1, dot, 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 a sub 1 times x plus a sub 0. So the a's are our coefficients. And in particular, a sub n, we're just kind of assuming here is not 0, because otherwise it wouldn't be a degree n polynomial. So let's let capital A be the sums of the absolute values of all the coefficients except for this top one. What we're going to show is that this x to the n dominates all of these others as long as we go far enough out. So here's the idea. Suppose that a sub n is greater than 0. It's either greater than 0 or less than 0. So we're going to do both cases. Then if let's set x to be the maximum of 1 and big A over little a n. And you're going to see why in a second. We get this. Okay, so I'm going to show here that p of x is greater than or equal to 0. And so how do we do that? Well, this is p of x. And importantly, we don't know whether these coefficients here are positive, negative, or 0. X we know is positive because it's at least as big as 1. So this is positive because we know this is positive. These things could be positive or negative. Let's assume all of these terms are negative, though. That's going to make it smaller or equal to the original thing. So how do we do that? We take these coefficients and we take the absolute value. This is now a positive thing that we're subtracting. So now we're subtracting all of these other terms and we've gotten smaller, if anything, than our original function. And then what I want to do is I want to say x is at least as big as 1. So x to the n minus 1 is at least as big as x to the n minus 2 because we've multiplied by x, another x. And same with x to the n minus 3. That's smaller than or equal to x to the n minus 2. So if we turn all of these things into x to the n minus 1. So I multiplied this by x, I multiplied the next one by x squared, I multiply this by x to the n minus 2, I multiply this by x to the n minus 1. All I'm doing is I'm making all of these terms larger. And since we're subtracting them, we're making the overall thing smaller. So that's why we've made this smaller. But the key point here is these all have a factor of x to the n minus 1. And this is how I figured out what this capital A should be. So this capital A is just the sum of all of these things. And so I just pulled out the x to the n minus 1, and we got this. And so as long as a to the n times x, well, okay, so we pull out an x to the n minus 1 from here. And as long as a sub n times x is bigger, than capital A, this is positive. And so what we've done is we've assumed that x is at least as big as a over an. Sorry for all the a's here. So we know it's greater than 0. And similarly, we're going to show that p of negative x is smaller than 0. Okay, so they're on either side. Now you might know this intuitively, but we're just showing it rigorously because this is one of our TA videos. So p to the negative x is equal to, well, we have a negative, because it's an odd degree, we have a negative x to the nth power. So I just pulled out the negative 1 to the n and made it a negative sign. N minus 1 is even, so this gets positive. N minus 2 is odd, so we get a negative, and so on and so forth. And let's do the opposite of what we've done before. We know this is negative, so let's ignore that. And so this thing, these might be positive or negative depending on these a sub n's. And so let's just assume, let's just make them all positive. And so we're making our overall thing potentially bigger. It's the same exact thing we did before, but in reverse. And again, let's take all of these x sub n's and multiply them by x again. Again, x is still positive. It's just negative x that's negative. So all these x's, we just multiply by these. We're just making these terms we add bigger. And so we're making the overall thing bigger this time. Again, we pull out the capital A from these parts. And then we now have this. And we factor out the x to the n minus 1, and we get the exact negative of what we got here. And so we know that this is less than or equal to 0 for the same reason as above. Okay, so that's what happened if this top coefficient was positive. What happens if it's negative? Well, I'm not going to show this, but it's exactly the same argument, basically. We would just flip them. If a sub n is less than 0, this would be bigger than 0, and this top one, p of x, would be smaller than 0. So you can work that out for yourself if you would like. But either way, we have p of x and p of negative x are on opposite sides of 0. That's the key to this problem. Okay, so by the intermediate value theorem, since 0 is in between these two values, there exists some x between negative x and x such that p of c is equal to 0. And that's exactly what we want. This is by continuity. We need to know that p is continuous, but it is because it's a polynomial. So therefore, since p of c is 0, that's what it means to be a root. And c is a real number. So c is a real root of the polynomial p. We've proved that every polynomial of odd degree has a real root. Okay, our second problem is much quicker, but we also use the intermediate value theorem in kind of a slick way, I think. So this is problem number 9. So let's suppose that f is a function from some interval to the real numbers. It's continuous, we need that for IVT. And let's assume this fact. F of the whole interval is contained in Q. What do I mean by that? I mean, every output of f is a rational number. So we can't possibly put in some value and get pi or some other irrational number. Okay, so you might think that this is not really going to work very well because continuous means you don't skip anything. And rational means we're skipping all the irrationals as we go. And in fact, that's exactly what happens. We have to have f be the constant function. And so we don't skip anything because we're not moving at all. So f is constant. So how do we prove this? Well, we just say, assume that it's not constant, and we're going to show a contradiction. So let's say that there are x1 and x2, two x values in this interval, such that their outputs are not the same. So we're assuming it's not constant. Now, These are two different numbers. One of them's bigger than the other. We don't really care which. But since the irrationals are dense, there exists some irrational number, which we're calling alpha, between f of x1 and f of x2. So if f of x1 is smaller, we have f of x1 is less than alpha is less than f of x2. And so here's where we use the intermediate value theorem. Since f is continuous, by the intermediate value theorem, there is some value c between these things such that f of c is alpha. Alpha is an irrational number, so this contradicts the fact that all of the outputs are rational, and so f must be constant. So I hope that was helpful. It's just a couple of examples of the intermediate value theorem. It's really a positive, a powerful tool that we can use in many different circumstances.